Okay, got an issue in sharing. I'll retry. Sharing is locked. Sorry. Do you see something?
No, actually. So
not
is
yet.
It like,
in general, okay, I never used this Meet, Google Meet. I'm not using those things
so you can just
far
go to present now and
because I'm sharing my entire screen and it fails. This one, no screen. I'm sorry.
Is there an issue about the permission given that?
no, actually I'm not getting any requests. So
I need to give authorization from my laptop, which I'm just doing.
okay.
I continue to allow all sharing options. I can confirm.
You need to share. You need to select the screen. You need to select the screen click on the screen and share it.
Yes, this is what I'm doing so far. Do you authorize to share? Yes.
You need to select the entire window.
And I guess this one will be fine. I got.
Yes, it will
here. You see what? You see my folders?
Yes.
Okay, so then, and if I go there, do you see the presentation or not now?
One second.
What do you see?
We were just seeing the folders, basically your screen.
So it's not that one.
Okay.
Hey, it's
okay.
Entire screen, the window. Okay, it is this one. Yes?
Yes, it's coming.
I guess yes.
Yes, it's coming.
It's coming. It's not yet in properly.
You can just go to the
Ignore.
presentation.
Do you see properly now?
Yeah, we were seeing your slides. You can make it full screen so that it will be better visible, I think. Yes.
Like this?
Yeah.
No. Okay, so I need really to go on my full screen. Okay, like this?
Yes. I think this should work.
Fine for everyone? May I start?
Yes. 1 second.
Let me know.
We are seeing your slide, but it is not yet full screen.
As for me, I see full screen. What do you see? I can remove that.
Yeah.
Is it better?
Yes.
The point is that I cannot, if I go full screen, presently here, I'm going full screen. I see my full screen. And do you?
Yes, now I think it's okay.
But we are not seeing full screen, but it is okay, I guess. It is okay.
Okay, because as for me, I'm seeing the full screen, so it's a bit strange.
Yes, we can see the upper.
I see what you see, but I don't understand why.
But we can see the upper tabs, like like the
Exactly,
red.
exactly. But this I do not. When I go here, you see my mouse or not?
Yeah, yeah,
Yes,
yeah.
yes.
You see, I will click here. Do you see diaporama?
Yes,
I
yes,
click,
yes.
and what do you see when I click that?
Nothing changed actually. So, but the screen is fine with us now, I guess.
Yeah.
Yeah, it is quite big here.
Okay. So if it's fine for you, let's go like this.
Yes, yeah.
But yeah, I have to check if I can. I have to switch on my PPT anyway. So, and here you see if I switch or not. If here, do you see the change of slide or not? Because
No.
I cannot follow directly. I have to. Okay,
No,
so there is a problem. Because,
Yeah. Now it is changing. Yeah.
Yes.
okay. So I will go this way. Okay, let's go. So again, so sorry for the small delay. So it's a great pleasure to give you a talk in the framework of OPTICA student chapter from IISER Kolkata, because actually this is really in the spirit of sharing fundamental of optics towards the potential of photonics for future development of science and or modern technologies in general. And I will try to give an example of it through a very specific approach associated with a subtopic of photonics related to the interaction between what we call the spin-orbit interaction of light that couple the different degrees of freedom that are the polarization state and the spatial degrees of freedom of an optical field. And as you can see in this title, it's not only about spin-orbit photonics from a fundamental point of view and discussing potential application in terms of technologies, but as well as shown here, self-engineered qualificative. I would like to show up how soft materials like liquid crystals could be used to produce, to design, to produce, and then to use in real application agile capabilities of soft matter in photonics. So for that, I will start by introducing some fundamental quantities that we will discuss on, and then I will move smoothly to the introduction of liquid crystals, and then we will go to the spin-orbit interaction as such and its application within the framework of liquid crystal photonics. And I will conclude by showing up a demonstration of what we can do with spin-orbit interaction of liquid crystal, that it's hardly doable with any other technologies so far. So then selling up the merit of spin-orbit interaction of soft matter in photonics. So let me start with general features of light. Even though some of you may have been already introduced to some of them, I'm restarting from scratch in order to provide the maximum of opportunity for everyone to enjoy from the beginning to the end. So I will start with defining the angular momentum of light, which is a quantity that will be there in all the next slides during this following hour together. Angular momentum of light, for that, I could provide with a very general framework. I mean, that covers all the situations. But instead of that, I prefer to restrict to a very simple approach in order to feel in a very simple manner, though relevant, physically speaking, of the angular momentum of light. So for that, I illustrate this with a beam in the dark, a light beam here, the red line, the red on the picture. And this line, by essence, implies that a beam is slightly diverging only. So like the output of the usual laser you could encounter in research labs or in student labs during the courses. And this means that a small divergence implies that this field, the light field, can be described within a very simplified manner within the paraxial Helmholtz equation. So within this paraxial framework, I just need to rely on a very simple equation, which is shown here, and that describes, I would say, moderately focused light beam in general, whatever their complexity at the level of low birefringence, they could be described by such an equation. And in that case, the electromagnetic field will be described as shown in blue here, an amplitude that depends on all degrees of the spatial coordinates, here taken in a cylindrical coordinate framework, times an exponential with a propagating factor, times the vector E, which is a unit vector here, a complex vector, which refers to the vectorial nature of light, so of the electric field, and which is called the polarization state. So this vector defines the way the electric field evolves in time and space. And here is a representation of the particular polarization state of light we will be interested in through this presentation, which are the secular polarization states, which are described by x plus or minus I times the y vector, divided by square root of 2 for normalization. With the two cases, sigma equal 1 or sigma equal minus 1, you will have the two representation that you can see on the left and on the right that respectively refer to left-handed and right-handed secular polarization states. As you can see here, the red arrows refers to the electric field position in space at a given time. So this is a snapshot of the electric field in space. And what do you see? You see a helical distribution of the electric field vector. And this helix, described by the tip of the electric field vector, described is either right-handed or left-handed, from which comes the name right-handed or left-handed secular polarization state. What is important here is that at a given place, the electric field vector rotates either clockwise or counterclockwise, depending on the handedness of the circular polarization state. And this, the angular motion of the electric field vector is reflected in the inner property of the quanta of energy for light, so the photon, which is associated with what we call an intrinsic angular momentum degrees of freedom, which is a spin quantity in quantum mechanics. And the projection of this spin along the propagation direction for paraxial light is simply plus or minus 1 times h bar, h being the Planck constant. And so this is well known since more than 1 century. And this part is really associated in a macroscopic way to the polarization state. Beside the spin angular momentum, oh, I see my animation are not working at all. It's a pity, but I continue like this. Independently of the, so we saw this vector, which is the polarization state, and there is also a second term I would like to comment on, which is the amplitude. And this amplitude actually, which is written here in a general way, without stating what is actually the light beam. In a general way, this complex function, I can expand it on a given basis. And if I choose properly this basis, I could choose a complete, exact, orthogonal basis. Mathematically speaking, it is an exact solution of this paraxial Helmholtz equation. And then every element are described by two indices, P and L, which are integer number, P being positive and number, and L being positive or negative integer number. So this amplitude coefficient, this complex amplitude coefficient is, you see in this general expression, is relatively cumbersome. But what is important here for us today is to realize that there is a factor in the middle of all those terms, which describe the curvature, which describe the so-called GUI phase, which describe the amplitude. There is a phase term that depends on the azimuthal coordinate phi, and which is a multiple of L. And this quantity actually is related to the possibility to obtain for each of these elements helical wavefronts. So then what matters here is a phase factor AEL phi, which corresponds either to left-handed or right-handed wavefront, helical wavefront, depending simply on the sign of the integer L. As it was the case for circular polarization state and the helical distribution of the helices for the electric field, we recognize again helix-shaped wavefront, so an helix-shaped morphology, this time associated with another kind of angular momentum, but not of a spin nature, but of an orbital nature. And here the word orbital refers to the fact that we are dealing with a spatial coordinate. By space, you see in general, a motion of something in space, we will call it the orbit of this something traveling. And here this something is a photon. And you have so a spatial quantity, the orbital angular momentum, so associated with the rotation. The orbital. Yes. Someone asked the question?
No, I think.
I heard something.
Yeah, please go.
It's echo?
Yeah, maybe someone's microphone got on or something like that.
Okay, so I continue. It was strange. I got some pop-up coming from nowhere, from my side. I don't know what do you see. It's strange. Do you see?
We could not see anything.
Yeah, we can see your screen.
We can see your screen
because
only,
I do not see what you see because okay, because I can't follow your. I do not see you guys. I see only my PPT, so I'm a bit disconnected from you, visually speaking. So okay. So you see this slide, angular momentum of light, defining a simple framework, yes?
Yes.
Okay. So the orbit, so then this defines the orbital part, which this one was much more recent than the spin angular momentum part. And this was typically now almost 30 years ago. Those helical wavefronts, you can, I would say, touch them if you go back home and look at some pastas, because some of them have the exact shape of helix, so the exact shape of the helical wavefront that you can hardly see with your eyes when you look at Laguerre-Gauss mode, for instance. So with this, you can convince yourself about how it does look like the equiphases of a Laguerre-Gauss component. And this leads me to introduce phase singularities. Why? Because in the central part here, I see, do you see my mouse?
Yes, okay. We can see it now.
You see here, all the phases here are equal because these are equiphases, and you have a lot of them for whatever number of phases you will have fixed. So on an on-axis, you have what we call a phase singularity, where the phase is undefined. And this phase singularity, actually, I would like to convince you in a couple of slides that it's a very common event. It's a very common manifestation of light fields. And to see that, let's consider a superposition of several plane waves. If you take one and you place a screen and you look at the intensity, you take a plane wave, it's constant intensity. And the phase depending on the orientation of your plane intersecting your plane wave, the phase will look like a ramp on your screen, if you can see the phase. If you take now two waves, you will have fringes, as you have usually when interfering two beams, for instance. In that case, you have some discontinuities appearing at the place where the amplitude is 0, which simply means that it's a signature of the fact that the amplitude of the electric field goes from a positive value to a negative value. In a complex world, this means that the phase has suffered a pi jump to get the minus sign. And this pi jump corresponds to a phase step. If you add now one more wave, you will have this kind of interference pattern, like spots, hot spots, and at the same time some dark spots here in dark blue. And those dark spots, those spots of null intensity, are associated with the emergence of points where all the phases meet. And these points are the location of phase singularities where the plane is undefined, and that is why they correspond to 0 of amplitude, since the field cannot express where the phase is undefined, because to define a field you need not only an amplitude, but you need also a phase. And this means that if you continue to add plane waves, not only 3, but much more, 10, 13, 1000, in general, what you get is so-called speckle field, which is a random field. And the phase is also random, but the skeleton of the phase is very well defined. It is defined by somehow bones, and every one of those bones corresponds to unit charge singularities described with such a local phase distribution, which can be either a 2 pi circulation around the phase singularity or a minus 2 pi circulation around the phase singularities. So those wave vortices are really constitutive of a random field in general, which means that they are very easy to observe, despite their I would say, fancy structure as such. Experimentally, for those who never experienced the phase singularity by their own eyes, I invite you to go to laboratory courses or research lab of some professors around you to use a laser beam, like a laser pointer, and a diffusive material. Here, I choose a translucent paper, and the reflection of light from this paper is random. And if you look closely, it will be like speckle light field. And if you add a reference wave, so you split initially your beam into 2 beams, one will be altered by the material you place in the path of the laser, and the second serves to induce some fringes. And if you look closely, where you have dark spots, you will have singular fringes events showing up a fork pattern with a local defect associated with the emergence of fringes, either up or down, which is a signature of the phase singularity of topological charge +1 or -1. So those pictures, I just took them with my phone to show you that they are very accessible to the lab. But in general, when you do not pay a special care, you will only observe plus and -1 topological charge optical singularities regarding the phase. But this does not mean that higher order topological charge do not exist. Actually, if you remember, the Laguerre-Gaussian expansion of a paraxial field contains all possible values for the integer L, which is the topological charge of the phase singularity expressed by this exponential factor. And they look like this. If you map the phase, we encountered so far those singularities, +1, -1, but you can construct all of them from -infinity to +infinity, each of them being locally associated with axisymmetric distribution of the electric field. And if you have only a Laguerre-Gauss mode, for instance, of this P equals 0 and L from -3 to +3, the beams will look like this, on axis 0, surrounded by light. So the typical signature of the phase singularity. However, those fields are more delicate to generate than simply with a piece of paper. You need something more to tame the light and to really induce some shaping which won't be destroyed by any residual other light fields that will compromise the existence of higher order phase singularities. This can be done as written here at the source, simply by shaping the laser cavity itself in order to generate vortex light sources. In that case, you simply have to engineer and design elements that will transform the radiation in order to force the radiation to oscillate inside the given cavity to a higher order, Laguerre-Gauss mode, for instance. Vortex lasers are emerging these days, and technologies are improving. But what remains the most common path to realize to have optical vortex beam in order to do research or to develop some applications. The idea is to use optical elements that you place in the path of the given laser source, which will be a simple Gaussian beam, as shown, for instance, in that picture. The two kinds of elements are the so-called spiral phase plates, which is very, I would say, a straightforward approach. The beam will pass through a plate whose phase depends on the location in such a way that it will wrap the phase in a helical manner. So with a prefactor, it will be a transmittance mask, phase mask, with exponential EL phi, L being controlled simply by the total amount of the phase accumulated around a full circle around the central part of the element. Of course, you need to have some criterion to match this, this wrapping by an integer number of 2 pi, and that's the job of developing material structuring technologies. The other option is to use diffraction in order to prepare gratings. As you know, gratings are diffracting light, and the diffracted beam actually is endowed by the information that has been encoded previously in the grating itself. Which means that if you prepare a grating pattern, assuming that you would like a given virtual beam, let's say an optical vortex beam, and you only have a Gaussian beam at home, you will compute the interference pattern between your Gaussian beam that you really have with a virtual beam that you would like to have, the vortex beam, and you will get this kind of pictures. And then you will manage, you will find a way, a technical way, to construct such a singular grating. And then this singular grating, you will illuminate it with your beam, the beam you already had in a lab. And then, that's the principle of holography, the diffraction will lead to the generation of the reconstruction of the so-called virtual beam. And then you will have generated an optical vortices from a Gaussian beam interacting with a singular grating. So a grating containing the information on the optical phase singularity you would like to encode on your light beam. Regarding the first option, the spiral phase plate, many technologies exist nowadays. From the macro scale, having phase plates, spiral phase plate, which are as big as 1 inch, for instance, so as a very usual macroscopic optical element, as the lenses you can use to form images with cameras and so on. But you can also do it at the integrated level using advanced 3D printing processes, and generating a microscopic spiral faceplate, as you can see here, which are two realizations that we did with our colleagues in Lithuania. You can also use this capability of engineering microscopic singular phase plates in order to functionalize other optical elements, like the output of an optical fiber. This is just the enlarged version. Appreciate the scale bar. At the tip of the optical fiber, where is the core of the fiber? So where is the light? The light will emerge from that part. And you can print at this very place a spiral faceplate. This is a step that you have pre-designed. And then you will generate the output of the fiber directly with a solid state, I would say, embedded technology. So you will have an integrated fiber optics vortex generator. These kind of things are actually already starting to be developed at I would say the scale of companies, as shown here in this example that I picked on the web. And of course, here I'm talking about singular optics and spiral faceplates, but spiral faceplate is a very common object, as well as a singular grating that you can recognize here as a typical shape of the fork. And this can be used to shape, I would say, any other kind of waves, not only electromagnetic waves, but also wave of electrons. For instance, the wave function of electrons can also be shaped in a way to have phase singularity for those functions, because the phase singularity are generic to all scalar waves, so to waves in general. Phase singularities do not need to introduce, for instance, as we are doing here, the polarization state of light. When I was presenting the phase singularities, I just need to have the information that the field that I'm looking at is a wave, and that's it, with a phase, described with a phase and an amplitude. So this applies to any particle, actually. As soon as your particle, you describe them as with a wave function, which you can do from a very fundamental point of view, then you can generate phase singularity for particles as well, such as neutron, as shown here in this sketch, which was shown 5 years ago, for particle physicists playing with phase singularity with neutrons. So this is quite fascinating to in my point of view. And it's important to recall that what we're discussing here goes beyond light. So it's beyond photonics, and that is why working in photonics will somehow open doors for other technologies, doing the appropriate analogies and the transfer of technologies and solutions. So after dealing with the presentation of spiral faceplate, which are robust, however, not reconfigurable, in the sense that once you have fabricated phase step, you have to deal with it. And if you want to change the topological charge of the vortex that you would like to work with, you have to change the optical element as well. So if you can produce those elements, this is very good, because you will simply produce another one. If you don't have them, either you need to order a new one, but this is okay if you can do this. What you would like to have, ideally, is a single element that could be updated depending on your will, on your project, actually, on what you want to test. And for that, there are equipments that are doing such a job. They remain expensive at the present day, but they do exist, and they do a great job in many research labs, which are the so-called special light modulators. And here, liquid crystal is one of the favorite material to develop this kind of elements that I will not describe. The idea that you have a device here, which is typically fits in your hand, and it's like a mini screen here, and there is typically 1 megapixel, so 1 million of pixels here, each of them being individually controllable with electric field, which is addressed via here these connectors. The pixel can be as small as 10 microns. And how it works it works by placing a liquid crystal in between two substrates. So what is a liquid crystals? For those who do not, who are not aware about those materials, liquid crystal is some material which is somewhere in between crystals and liquids. So why in between? Actually, because as you can see on your left, they are endowed with the orientational order of crystals. At the same time, they are endowed with the positional disorder of liquids. So that's why marrying these two words, you get liquid crystals, which actually corresponds to not simply mixing two states of matter. It's a new state of matter. And this was well described by the physicists during the last centuries. The way that so it's like 1 century ago that it has been really like understood that liquid crystal represents another state of matter, and we are speaking in general about mesophases, which are, if I translate, intermediate phases, but genuine as such. And liquid crystals, which are generally composed by anisotropic elongated molecules. This is why I was plotting here ellipses, elongated ellipses. And if you look locally, a bunch of molecules, the classical liquid crystal, the one that they are usually in your screens, if those are based on liquid crystal technologies, they are filled with what we call the nematic liquid crystals. And nematics, they got these following properties. If you look closely, a collection of molecules at the small scale, each of them tends to be parallel to the neighbor, to its neighbor. And this defines locally an orientation, which means an arrow, but there is no head or tail. That's why there is a double arrow here. It's a kind of stick if you want, which is called the director, and I will use this vocabulary, so on. Which is usually called n, the unit vector n, which define locally the average of the orientational order of the molecules. So the material is at the macroscopic level described by a field, by the director field, the n, that can vary in space, but also in time. And as liquid crystals are made of elongated and oriented dielectric molecules, these make such fluids birefringent. So not only they are birefringent from an optical point of view, they are optically anisotropic, they have a dielectric anisotropy, and they are as well reconfigurable, because remember, it's a fluid. So you can easily modify the orientation of the molecules, because you can make not only the fluid to flow if you need, but you can also orient this fluid as well. And this can be done by using electric field in particular. If the anisotropy is positive, which means if the dielectric property is larger along the main axis of the molecules than along a direction perpendicular to it, it will be positive. If it's the opposite, it will be negative anisotropy. And in these two situations, the tendency to be oriented when electric field is applied is the following. For positive nematics, the molecules, the director field will align parallel to the electric field. If it's negative anisotropy, the dielectric torque exerted by an electric field on the material will make the molecules to rotate on average in a perpendicular direction to the field. And these two situations we will exploit in the following examples. Here, back to the special light modulator based on liquid crystal technology. And let's see how it works. You have two substrates here, and I'm looking the pixel from the side. The molecules are arranged, say, parallel, so in the plane of the screen here, of my screen, so of your screen as well. And the light is passing here. The light is linearly polarized and passing through the system at rest. which means that the phase will be accumulated by simply reading the refractive index along the major axis of the liquid crystal, which will be n parallel in that case. And if we apply an electric field for a positive dielectric anisotropy of the liquid crystal, then, as we just showed the slide before, the molecules will tend to be FA-oriented. If the electric field is polarized in the plane of reorientation, which is the case here in this drawing, the electric field of light will read this reorientation. And this reading will be manifested in the phase accumulated as the light passes through the pixels, which means that varying the voltage between the two substrates in which is sitting the liquid crystal, you will be able to modulate from one point to another on demand the phase of the output light field. So you will be able to shape any phase profile that you want. And this phase profile will be dependent, of course, on the wavelengths that you use. So there are chromatic limitations, which you cannot, you have to deal with that. However, in some circumstances, typically if you want to develop some techniques which are insensitive to wavelengths, you would like to have something which is non-chromatic. In that case, you need to call another kind of physics that will drive us to the so-called spin-orbit interaction. The idea is that if you do not want to suffer from chromatic effects, you do not want to depend on propagation effects. So the idea here is to exploit something that does not depend on propagation through a structure, but to the structure itself, to the material itself, so to its geometry. To understand that you can do such a job, here is a qualitative slide, and the idea is simply to consider the right-handed and the left-handed circular polarization states, as shown by the two colors here in red and blue, and to consider a rotation, a local rotation of the spatial coordinates. So you go from the gray frame to the dark frame by an angle phi. And if you look at the phase in the reference frame of your choice, you will have that depending on the right or left circular polarization state, the phase that you will read, if you have a phase meter in your hands, will be different by twice the angle of the rotation phi, the phase difference between the two polarization states. And this corresponds, qualitatively speaking, just to catch what's going on here. It's a kind of time zone effect, if you would like to picture it mentally. Depending on the place you are, you will have different time, which means you will have different phase. So this is exactly, the analogy is quite powerful and allows to understand how phase could differ depending on spatial rotation of a coordinate system. And this implies that if you are using a structured material, and before using any structured material, let's consider an anisotropic material. As shown, represented here, the direction of the anisotropy here by these gray bars, which corresponds to the, let's say it corresponds to the slow axis of the half-wave retarder. The half-wave retarder will transform an input right-handed circular polarization state into a left-handed circular and the opposite. The left will be transformed into the right. Because it is dephasing orthogonal component of the electric field by a phase term, which is pi. And by flipping the polarization state, what you see here is that the phase relationship between the two circular polarization depends on the orientation of the wave plate. Because it's exactly that time zone effect, that geometrical effect of described just here, when you rotate this, the coordinate frame. Which means that if now you are structuring such an optical element, a half wave plate, for instance, you can simply control the phase from one point to another, irrespective of the wavelengths that you used, as soon as you have an active plate retarder. In that case, you can encode wavefront, which depends on the spin. And that's the particularity of this interaction, the spin-orbit interaction, because with the polarization state, so the spin degrees of freedom, you can control the spatial dependence of the phase, which is the orbital component for the light field. And here is the emergence of spin-orbit photonics, and this has been introduced quite a while ago in optics by Bandari, almost 25 years from today. So still, as I was mentioning, you need to satisfy this half wave plate condition. So there is anyway a chromatic issue if you want to be fully efficient in terms of recovering a field that will be endowed with this encoded phase profile into the structure of the material. So if you want to generate optical vortices, being in the framework of angular momentum of light, in that case, you simply need to shape appropriately this optical axis distribution in such a way, half integer or integer times the spatial azimuthal coordinate, because in that case, the dephasing will be simply twice this local angle, and then you will have a topological charge will be equal to plus or minus, depending on right or left-handed input circular polarization, and twice this structural topological charge of the material that you are dealing with. So you have access to a spin control topological charge, so which means spin control of the sign of the phase singularity that you have generated. Where comes liquid crystal here? Liquid crystal actually have been used, have been recognized very soon after the understanding of this spin orbit opportunities to shape the phase in a controlled manner, implying the polarization state. As liquid crystal have been recognized as very good elements to do that, because it turns out that it is relatively easy to orient them. For instance, by rubbing substrates in order to show you are simply like really rubbing mechanically some substrate in order to induce like micro grooves, and then the liquid crystal tends to follow those grooves in terms of their orientation, and you can generate, for instance, here in this case, in this early case, 15 years ago, circular patterns of liquid crystal orientation that will lead to the emergence of twice the structural charge, and you will observe twice this value, so plus or minus 2, depending on the incident spin in the generated optical vortices, here unraveled by interference with a coaxial reference beam that will break the usual circles of a Michelson interferometer into double arm spiral interference patterns. After that, soon after that, the couple of years after, photoalignment techniques were emerging and were used, and actually were further developed in order to encode arbitrary pattern into to the substrates in order to fabricate element. And you can appreciate this is a really macroscopic element, typically 1 inch square, in order to structure at will the singularity of matter, the singular orientational pattern of matter, in order to generate optical vortices with on-demand topological charge that depends on the fabricated element. However, if you look closely at small scale, not at the centimeter scale, but at the micron scale, so here the distance between the two guys here is roughly about 100 micron, so this was 10 years ago. The topology is small, is lost, sorry, at small scale, which means that the quality of the charge here is very hard to define and to print with a good quality. But this was 15 years ago. And nowadays, at the micro scale, some companies can deliver very high resolution static liquid crystal optical elements on one side, and but they're very expensive. On the other side, more, so I would say, more popular and more cheap products, which are anyway expensive. They're typically there are several hundreds of euros each. However, it's kind of compromise between accessible optical elements and reasonable resolution, which means the quality of the design is ensured at the scale of a few tenths of micron. However, this is static. If you want to have tunable, so if you want this capability that can offer liquid crystal a priori to be reoriented, then they are low resolution. So can you combine all the assets? So you take the best of the two worlds to generate kind of new devices. So the idea is that this is what we were doing in our group since several years, is to combine all these assets into a single device, exploiting the capability of self-organization of liquid crystals. Because remember, the molecules of liquid crystals tends to be locally parallel one to another, which means that you can manage to tame matter, just to drive it into situation where there will be self-organization around structural, material, orientational defects without the need of artificially writing these structural orientational defects. If you succeed to do that, you will have access to a self-engineered route, so self-engineered technology, developing spin orbit photonics. So this is what we started 10 years ago, actually. This was the beginning of story, using droplets of liquid crystals. So the idea is simply to mix a big macroscopic droplet into water plus some soap. You mix and stirring and shaking, and you get microscopic droplets. And those droplets, once trapped into optical tweezers, we were showing that you can generate optical vortices out of them related to the existence in the central part of the droplet of a structural orientational singularity. And here is the recipe that I was explaining before. Then I will go faster from now that we catch this recipe. Structural orientational singularity can be then transferred to light via the spin orbit interaction. So you have a defect here, which is the topology of a structural charge Q equal 1. Then you can generate optical vortices plus or minus twice this value, so plus or minus 2. However, they are limited efficiency in the sense that a droplet is not really a half wave plate. An half wave plate condition is the optimal condition, because in that sense, all the spin flipped photons will be properly phase patterned, which means all the input energy will be transformed in the way you want in terms of the phase profile encoded into the structure. And since a droplet is uneven thickness, depending on the place where light is passing through, you can't satisfy for a given wavelength, you cannot satisfy the half wave plate condition for all the field. Which means that if something needs to be improved, it is the control of the birefringence phase retardation that is limiting the efficiency. So for doing that, we were using planar substrates, no longer droplets, so films of liquid crystals, initially oriented in such a way, perpendicular alignment of the directional field with respect to the substrates with negative anisotropy. And in that case, if you place a voltage difference between the two substrates, you will have reorientation in a perpendicular way with respect to the generated electric field. And since there is azimuthal degeneracy, because you start with a perpendicular alignment, it can go in a perpendicular direction, but with all azimuthal direction. And at some places, you will have defects. And this is the picture here between cross linear polarizers. At some position, you have, you see crosses, dark crosses, which are actually the signature of defects, which can be either of structural charge +1 or -1, and the local orientation in the neighborhood of these defects are represented here by this white line. So +1 is star-like and hyperbolic 1 for -1. And these two kinds of defects can be used as microscopic, look at the spatial scale, 100 micron, microscopic optical vortex generator, which can be tuned simply by changing the voltage that has given birth to the defects themselves. So not only the voltage is here to structure the material, but also here to tune it. So these are electrically tunable, self-engineered optical vortex generators. And the idea is to tune this birefringence phase retardation in order to reach this full transformation from an incident circular polarization state here, sigma, into the contra-circular polarization state when the phase condition here will be pi, which is the half wave plate condition. In that case, the first term is vanishing, and you are left with a pure phase shaping of the output light field. So in general, the efficiency will be simply defined by the amount of energy that is being transferred into the spin-flipped component of the output reflecting field. And since this quantity can be controlled by simply the amount of reorientation of the liquid crystal, you simply need to change the applied voltage in order to transform your incident Gaussian beam either into a vortex beam when the efficiency is maximum, this corresponds to half wave plate condition, or to a minimum, in that case there is no transformation, even though you are passing through the defects. There is no reading via the spin-orbit interaction of the material structure, and the output is simply a Gaussian beam again, as in the input, when the phase, birefringence phase retardation that is experienced by light is a multiple of 2 pi. I show you here a video to illustrate what's going on in the lab. Here are the Michelson fringes, a Gaussian beam with a reference. And here simply, you see, my arm was coming here, changing the voltage, going to the wave plate condition. And then you observe the spiral plate, the spiral interference pattern. And here, the next switch I did is simply to control the voltage between two values, let's say 2 pi and 3 pi, and to oscillate. And in that case, you have a time control of the vortex generation. So I would say on demand, when you need it, you simply need to activate it electrically. So it's controllable also in wavelengths, because you can simply also adjust your voltage to the used wavelengths. So it's controlled in wavelengths, it's controlled in appearance or not, it's controlled in efficiency. However, we are only dealing here with those particular defects I was showing to vortex, optical vortices ±2 regarding topological charge. And here is the situation, again, calling nature to solve this problem of topological diversity, because nature exhibits a various amount of topological manifestations, and simply by changing, this is just an example, simply by changing the alignment from perpendicular to parallel, you can generate as well, if you have a degenerate parallel alignment, which means that the molecules, you do not dictate in advance how the orientation of the molecule is in a plane, could be random. There is a spontaneous organization, a self-structuring of the material into a wide number of defects. Here I show 4 kinds of them here. 2 branches or 4 branches that corresponds either to half integer or integer values, all of them spontaneously appearing. And again, you can tune them simply applying an electric field, in that case with positive dielectric anisotropy material, in order simply to change the birefringence phase retardation and to tune according to the used wavelengths. And here this demonstration of optical vortices from -2 to +2, and we even extended this range in further works. And their interferential characterization, and you can see the spiral, either right-handed or left-handed, depending on the sign of the topological charge of the generated optical vortices. So, stating that now we have somehow addressed the topological diversity limitation, what remains to be improved? That's my question. And at that moment, I would say the randomness of the appearance of this topological material structure was the limitation. Because even though they were spontaneously and nicely emerging from nowhere, from a uniform background after the application within an external given configuration, either application of a field or simply nothing, in the case we are seeing here. The size and the location were really not controlled. The size, I mean the interdistance between two defects. So to cope with these limitations, and much more recently, my proposal was to direct and to control at the macroscopic level the self-organization down to molecular scale, or to combine the macro world with the nano world in a given optical element in presence of self-organizing material such as the liquid crystals. The idea is here. Let's use a magnet, and this is a rig magnet seen from the side. Using this magnet, here is a picture of the magnetic field line, and this magnetic field line looks like a kind of a fountain. You see water emerging out of a pipe. It will flow like this, and these are the magnetic field line. If you look from the top, what you will see is something like this, star-like projection of the magnetic field lines, which means, speaking about structure and topology, this will be topological charge 1 structure of the projection of the magnetic field line in the transverse plane. Which means that placing this magnetic field below a planar liquid crystal layer, exactly the same one we showed before that was giving this kind of random distribution of ±1 defects. You place the magnet. The magnetic field of this magnet is also contributing to reorientation, magnetic reorientation of the liquid crystal. Very, very small, but it is there. And this is somehow seeding the material. And we don't see the video here. I'm just checking. No, we don't see it. It's a shame. There is the point is that you start from a situation where it's unreoriented. You approach the magnet between cross-linear polarizers. You see simply nothing. It's dark. And then if there is no magnet and you turn on the voltage, you have random appearance of defects. Now, if there is a magnet and you start from 0 applied voltage and you turn on the voltage, after a few tenths of seconds, so below 1 minute duration, you have the emergence of a self-structured macroscopic optical vortex generator. So you have an optical vortex plate that will be further controllable electrically, as we shown in the example before, and you can control it whatever the incident wavelengths you need to proceed. So here I was demonstrating in a visible region, but you can extend it to the infrared without any problem as soon as you have infrared source, because liquid crystal is also very well birefringent in that region. So this is what should be remembered, and of course the characterization of these elements were done, but here I would like simply to insist on the chromatic control of this macroscopic plate. However, again, it is not the technology is the one of nature, I would say. It is a self-structuration. And I would like to end, if times allow, but so I know we had problems, so let me know if we can continue for 5 or 6 more minutes.
Yes,
me know
we
if
can. So,
we can.
yeah.
And then I would like to on a given example, which will be the astronomical imaging, I would like simply to convince you on this imaging kind of application, how self-engineered spin orbit photonic technologies made of liquid crystals could be used to make real some idea that would be very hard to fabricate, to realize otherwise. So the context is observing the sky. So let's say we are all astronomers for the next 5 minutes. We're interested by looking at the stars. And let's have a look at night at the Sirius star. It's very bright in the sky. And however, there is a companion of Sirius. And this companion is here, but you don't see it with your eyes. You don't see it because in a visible domain to which your eyes are sensitive, it is 10 to the 4 times less bright. So you simply don't see it. But remember, we are astronomers now, and we would like to see it because we're interested by this small companion because someone told us that there is a companion star nearby. So how to do that? One of the options is simply to abandon our eyes and to replace the sensor with a sensor sensitive to another wavelength range. And I will click. And here I'm switching to X-rays Google's filters. And this is what you can experience if you have X-ray observation of Sirius. The main star is no longer, you see my pointer, my mouse is simply very faint, is fainter. And the secondary star of this binary system is now the brighter. So of course, this is not very convenient because you need to be aware about which kind of filter you need to use, which kind of sensor you need to use. But of course, this knowledge accumulates with time and exploration of astronomers and techniques. 80 years ago, a guy, an astronomer, was somehow a bit annoyed by this situation, as many others of his colleagues at that time, in a sense that if you want to look at bright things and you want to look at details, like here the companion of the star Sirius, or the corona of the sun, for instance, which is very faint structural features, which you cannot see directly because you are blind by simply the solar disk that you simply blind your sensor. And how to study corona of the sun, for instance, is simply to wait for the total eclipse by the moon. When the moon is passing in between Earth and sun, in an appropriate way, you will have a total eclipse. And in that case, you will be able to study the corona. It's simply like placing a screen on it. But to make such observations, you need to be very patient. And upon a lifetime, you will have simply, I would say, a couple of observations. So it's quite frustrating. And Bernard Liot, a French astronomer, so 80 years ago, decided to devote his time to develop apparatus in order to create, in an artificial manner, eclipses. The idea is simply to mimic what the celestial mechanics, and simply to place an obstruction in a course of a bright field that you would like to observe from Earth. So the idea is that the observation tool being a telescope here, I simply replaced it by a pair of lenses which mimics a telescope. The two main features of a telescope, a collecting lens and then a recovering lens. There is the aperture of the telescope here on the left, and let's say here the sun is going from left to right, being focused and then being re-imaged on the camera, and then you see the sun. Leo says that, okay, I would like to mimic celestial mechanics. I will place my moon, which is a small obstacle, in a Fourier plane of the telescope. This way I have an absolute eclipse. And then down, I can observe corona very easily, and this is what he started to do. And he did very nice improvement of the understanding observational of the corona of the sun. However, light is not like my drawing, which is a geometrical picture. Light is a wave. And light cannot be confined to a finite size in a sharp manner simply by focusing it by the lens of the telescope in a Fourier plane of the telescope. You will have an airy spot and you will have tail leaking out of the obstacle, or whatever is the size of the obstacle. So in general, what you have is not exactly total eclipse. It will be intermediate one, but still working nice enough in order to do the job. And here come the vortexes. So here come the optical phase singularities, because much more recently, I mean, it was 15 years ago, only 15 years ago, it was realized that instead of placing an obstruction, which is an amplitude mask, in order to create artificial eclipses, it was suggested to use phase masks, but not any phase masks, vortex phase masks. The very phase masks we were discussing on during the last hour. And the idea is that if you place, this is a mathematical exercise that I propose you right now, you place this vortex phase mask of charge 2, plus or minus charge 2, in a Fourier plane of a telescope. This phase mask is not obstructing photons, it is simply imparting a phase to the photon, a phase to the airy spot in the focal plane of the telescope. The point is that an airy spot multiplied by such singular phase masks, after propagation down to the output exit pupil of the telescope, the redistribution of light nearby this very plane here is like this here. This is this dashed line for the meridional cut, and here this is a transverse distribution of the intensity. The light is totally rejected outside the geometrical image of the aperture here, which is a disk. So this comes from a mathematical property of the Fourier transforms associated with this optical, very simple setup. Based on this fact, the fact that placing a phase mask with topological charge 2, you can recover in a given plane a total, the total redistribution of light outside a given area, which is circular. It means that placing a diaphragm, so an obstruction that you will close enough in order to only capture this area, which is without any photon of the incident on-axis light that you would like to observe, the one from a star, for instance, everything will be suppressed. And then you have really an artificial total eclipse. Once you realize this from a mathematical point of view, you simply want to place such engineered phase masks into the telescope. This is what is done here with the laboratory demonstration. And you have an eclipse of the star, which was a greenish, so it's saturated. You see it white, which is almost not here. So in the presence, without the mask, you see it. This is the mask, you don't see it. What is this second reddish spot? This is the second light beam, because this is laboratory. This was made with laser beam, mimicking distant point source. And if you enter with an angle, the airy spot in the Fourier plane of the telescope will be slightly off axis the singularity. And this operation, this optical transform that reject light outside the disk won't operate anymore. So this light, this off-axis light, will be able to pass through the system as if nothing was around. And then you continue to observe it. Which means that you can selectively suppress any point source that you observed in a given direction. Which means that you can look at faint celestial objects nearby bright sources. What does it mean in practice? It means that this is a tool to directly observe the photons coming from exoplanets. Consider a distant star with a nearby orbiting planet. Let's say you have a distant star-planet system, and you would like to know more on the exoplanet. You would like to collect some photons from there, and then to do spectroscopy, to see whether there is an atmosphere on this exoplanet, and so on. The quest of the second another Earth, as you are, I guess, all aware as scientists interested by general developments. Exoplanets is something I'm sure you already heard about that. And to have such a tools that could retrieve to extract the photons from the very exoplanet without being polluted by the photons from the star is of primary importance for study of exoplanets. So those tools were really amazing at that time. So really 15 years ago, it's very recent at the scale of the research. And from the lab, a couple of years after, it went to observatory. Again, a binary star system was observed. Here you see a bright sources. Off means that there is no vortex activated. And here, very faint source. You activate, you extinguish the main source, and the other one is appearing in the background, from the background, and then you can observe photons, and those photons are not polluted by those ones. And the improvements were improving every years. And here is the first exoplanet check that it can be detected with vortex coronagraphs from a ground-based telescope at Palomar Universe Observatory. And now NASA is continuing developing with this team optical vortex coronagraphs of better and better performances. And nowadays they look like that. And those elements, which are centimeter diameter, these are diamond nanostructured plates. So you see it, the macroscopic version of it, microscopic version of it. You recognize arrays at the sub-micron scale. So this is working for an infrared. And for the infrared, such a sub-wavelength structuring is inducing a structured birefringence, which is tuned to be half wave plate. And you recognize axis symmetry, which is the signature of the topological charge for the material structure Q = 1, that will generate via spin-orbit interaction an optical vortex of charge 2, the very vortex we need to implement optical vortex coronagraphy. So that somehow closes the story in a sense that researchers have developed technologies based on spin-orbit interaction in the spirit of addressing a fundamental question for humans, let's say, the study of exoplanets with photonics. However, those elements are, of course, state-of-the-art elements. They are static, fabricated once for all. There are only a couple of pieces for a given telescope. However, they are present in all major ground-based international telescopes, even though they are limited to infrared at the present day, because it's very difficult to get very high quality, very large surfaces with submicronic structuration. And here comes the liquid crystal. Because when saying that, and having at hand self-engineered devices, I was wondering whether I could do something there by injecting some agility to some new performances for new opportunities in that field. And taking a picture from Star Wars movies that I guess at least several of you already saw, this picture, which is dating now, but with a binary sunset. And this is my question. Could we use these self-engineered liquid crystal plates to get vortex coronagraphs that cannot only simply doing the job for extinguishing one star, as we were showing here in the lab? This is from a liquid crystal coronagraph at work, a vortex coronagraph of liquid crystal defect, without any technology. It's spontaneously generated, and it works very well. But for several stars, even the question is very provocative from astronomical point of view. Could we study a multiple star system with vortex coronagraphy? And the answer was yes. We actually demonstrated a couple of years ago such a demonstrator in the lab. And this is the last slide, so I will comment it. The idea is that we were using a nematic, the very same as I was presenting before, to get the charge 1 topological defects between glass as a substrate as before and between another substrate, but this time it's no longer glass. It's a photoconductive crystal. And this photoconductive crystal allows to develop multiple optical vortex coronagraphy. Or it is possible to do that. A photoconductive material will change its electrical properties depending on the received optical intensity, which means that where there is light, there will be, say, more electric field in the presence of a given applied voltage difference between the two substrates. Which means that if you are sending multiple beams, we don't see the beams here because of the, like this, we will see. Imagine you have different stars, S1, S2, Sn, like this. You have different stars, distant star. You want to observe in a Fourier plane of a telescope, which is here. So you see hotspots, the airy profile of the 3 stars you would like to extinguish at one, all at once. We will send 3 writing beams in order that the airy spot of these writing beams will exactly fit on those airy spot of the star you would like to extinguish. This will change locally the electric field, the electric properties of the material, which means that if you manage, you prepare the system properly, the liquid crystal will be reoriented only in those areas and will be reoriented in a way that liquid crystal defects with charge 1 will appear, and they will be exactly centered. Then, once you satisfy this condition and you tune it to have optimal vortex generation, you will have optimal rejection, and this is what you have. This is in log scale. You can appreciate the almost 4 decades, and the images are normalized to their own maximum of intensity. This is the initial image where we place a 4th beam, which is, let's say, our virtual planet, which is almost unseen. Remember, there are almost 4 decades between the maximum. And you simply activate the vortices with your controllable, let's say, moons, if you would like. It's a kind of controllable moons. And you can selectively extinguish one by one all of them in order to have the planet appearing, and then ability to collect the photons from this very single direction of observation that you would like. So this is my take-home message to conclude, is that soft matter And the topology it can express in a natural way or a directed way, because soft matter is very sensitive to any external constraint. Then you can develop, by properly taming the field matter interaction, a self-engineered approach to spin orbit photonics, and developing not only a fundamental knowledge of topological interaction between light and matter, but also developing at least new proposal, and perhaps for the future a real new application that will be useful in a wide range, for a wide range of communities. And this ends my talk. I thank you for your attention, and I'm keen to take time with you guys for discussing about any questions and other comments.
Thank you, Professor, for this wonderful talk. So now the platform is open for some questions. So if anyone has any questions, please raise your hand and unmute yourself.
Hello, sir. I have one question. So, can I ask?
Sure.
Formation of a speckle pattern after the fiber when light pass through it. So, how topological charge play a role in the formation of a speckle pattern?
So speckle.
That are in the beginning of.
Here?
No. Just one slide and back. There.
This one?
Yeah. This.
Which one you? Okay. So yes. So
formation of a speckle pattern. No? So how this vorticity that e raised to power I alpha and orbital angular momentum play the role in the formation of a speckle field.
Here it is the speckle itself, because here what I plot here, this is the intensity profile, and this is the corresponding phase profile. So my message here is that take a random field, interference between a random set of plane waves, different amplitudes, different orientations. This is the field you will get. You will get a random distribution of hotspot, and there is statistical distribution of the intensity associated with speckle field physics, and this is the phase associated phase, which means that it's really they are connected, these two. There is no mutual influence. That is the field.
But I can't understand the this topological charge, how it's play a role the formation of these ones. My question.
Your question is the same as, I mean, if I understand correctly, you are asking me how the vortex here are playing a role in the speckle, but the vortices is shaping the nature of the randomness, not only of intensity, but there is also a random distribution of phases. And when you have a random distribution of phases, you cannot escape the emergence of phase singularities.
Okay, thank you.
And you have an example here. It is something you can play with if you have any software capability resources. If you have software resources to compute the interference pattern between three beams, three plane waves, you just take three plane waves and you make them with the arbitrary angle between them. And if you plot the intensity of the total field, you can even write it analytically, I would say. And to evaluate, you take the magnitude of your field, you will get something looking like that, hotspots. And if you look the phase of your complex field, you will get phase singularities. So they are really emerging as soon as you have 3 plane waves. So they are very constant. I got a lot of echoes. I'm listening.
So Athira, you can go ahead and ask the question.
Thank you, Professor Brasselet. It was a wonderful talk. So out of curiosity, the work that is related to the application in the exoplanet detection, if in terms of occulting disk, that is what a vortex coronagraph does. But the occulting disk, the size matters, in which the size is here is described by the topological charge of the vortex generating material. But how do you design what kind of topological charge we need to occult the main bright star in order to observe the dim object or the exoplanet system?
From a general point of view, the need to get this, you need even charge. I was only focusing on charge 2. In general, let's say the recipe is even topological charge. What you need to have is that your even topological charge should be phase singularity for the mask should be at the very place where is the airy spot of the distant light source you would like to reject. So there is a double condition. You need a phase mask with even topological charge, and its center should be overlapping with the image of the star in the Fourier plane. That's the only recipe you have to follow. And then when we were using the liquid crystal, the idea was to generate at the place where is the star to be occulted, to generate the charge there. How we were controlling the charge? We were controlling the charge via this specific use of the photoconductive element, because here we're in the Fourier plane here, this writing beam, which will act as the vortex local mask, is generated also by a airy spot of the writing beam, because it is also in the focal plane of the telescope for this optical arm. And when you have a Gaussian beam, what you will have here, you will have a Gaussian modification of the electrical property of the photoconductor, which means that you will have a Gaussian local redistribution of the electric field, which means that you will have the excitation of the reorientation of the liquid crystal in an axisymmetric manner, in a Gaussian-like manner, if you prefer. And this axisymmetry is reflected in the emergence of a topological charge 1 for the structural point of view, which will lead, after spin-orbit interaction, to an optical vortex shaping with the topological charge 2, which is the one that we want. And when we were doing the first demonstration here with a single defect, this one was picked from a random collection. We were generating a set of defects. We don't know exactly where. We were taking a good one and we were placing in a central place of in a on-axis position with respect to the telescope. It was doing the expected job as shown here in this slide.
In that case, can we also follow the same recipe for occulting the sun to observe the atmosphere of the sun to create an artificial?
Exactly. Here, when Leo was doing the job here, he was placing an occultor exactly in the place of the airy spot. Exactly. But and as you said in your introductory part of your question, the size of the occultor for this amplitude shaping is important, because if it's too small, it's not good. If it's too large, you will have no light at the output. There is an optimal trade-off. But in case of optical vortex coronagraphy, which is made for distant light source, the sun is not like that much distant. You see, it's not a point source. You see the corona is the external part of apparent surfacic region, the area of the sun itself. And when you do optical vortex coronagraphy for exoplanet observations, you are really dealing simply with the equivalent of point source from optical point of view. And in that case, this mathematical description is nicely applying, and that is why the technique is working well.
Thank you. Thank you.
So I have some questions, like when you showed that when we have a parallel or perpendicular alignment of the liquid crystal, let's say for homotropic and heterotropic alignment, there itself we have different vertices with different topological charges like Q equals to half and Q equals to 1.
Yes.
So for me, like in normal, like if we see the director orientation is parallel to each other, or they don't have any special anisotropy. So in this scenario, how can, means like why we are having this type of vertices? And
here?
Yes.
In this case, okay. So let's take this situation, okay? So do you see, since I don't,
yes.
You see me properly. So you see the two substrates are like this. It's important to imagine my fingers will be the molecules, are the black stick on my screen, okay? These are the molecules. The two substrates are here. And it's degenerate. When I say there is a degeneracy, it's because if you look from the top, what you see is this. You see all the molecular directions like this.
Okay.
And there is, now you applied an electric field along this direction. And it's negative anisotropy, which means that this is the electric field, this is the molecule. I apply electric field, and the molecules tends to be reoriented in a perpendicular manner to the electric field, which means like this.
Yes.
However, the starting point is vertical, is exactly parallel to the initial electric field, which means that it could go like this, but it can also go like that. It can go like this, like that. So it can go in all the direction. This is the meaning of the cone here. You can be reoriented. The reorientation plane can be arbitrary. And because of that, you will have different places in a sample where at some places, because of some thermal fluctuation, because the molecules are not at rest, everything is at thermal equilibrium. So the orientation of the molecule is like this, slightly dancing with time due to thermal effects. And at some places, when you apply the electric field, the fluctuation will be in that direction, and then will be reoriented in that direction. In another place, it will be another direction. It will be reoriented in that direction. But at the end, the system needs to close on itself. And at some places, there are some problems because you need to address all the direction at the same point, which means that the system is not reorienting at that place. And it leads to the appearance of a defect as shown here. It is really the result of a degeneracy. And it is because there is a degeneracy that you can have the topological structuring in a natural way. You don't need to force the system to structure. The system has the ability of structuring because it is degenerate. And so it can explore all directions. So it is very essential point, the degeneracy.
Okay. So now if let's say we have different queues in in different space, and I am evenly illuminating, let's say it's like we are illuminating with the optical beam. So the beam will have different vertices at different, like it will different vertices with different topological charges will generated at different place, right? So is
If
it okay? So is it not going to, like, if I want to generate some vertices with a particular queue, is it not going to effectively dilute the uh,
good point. Oh, good point. So you have this collection of defects in this case, and you want but you want let's say a single device. So what you need to do is you need simply to restrict yourself to illuminate the sample, let's say, around that place. So you need to target it. So you need to know where is the defect before to use it. And this is why I was mentioning here, even when in the case where you can generate other kind of values for topological charge, it is limited by randomness of the generated structure. And this randomness is a limitation in practice because okay, the structure is very easy to fabricate because it's naturally fabricated. However, you don't know where it is fabricated. So you need first to observe and then to align your optical element to your beam. And that is why the further developments, for instance, here using the magnet, but we developed also other options where you can predetermine the very location where will appear the defect, and not only simply with a random distribution from which you have to extract a particular place to do the job. So the idea is to develop external field control. It could be magnet, it could be electric field, it could be the light itself. We also demonstrated that the light itself can be used to generate its own vortex plate via the generation of a defects. So here is just an example, but in general, the spirit is you have an external field. If you are cleverly managing the light matter interaction and the light field interaction in the field matter interaction in general, magnet, electric, optical, combination of everything, you will be able to tailor the emergence of topological self-organization. And it is what we are interested in developing.
So one last question regarding the optical vertices generation from liquid crystal droplets. There you mentioned that you are using, like, you are tweezing the droplets and you are seeing the generation of the vertices. So
Yes.
is it necessary? Like, why this step is needed? It means, like, why you have to tweeze the liquid droplets?
So I was here using a tweezer in this very first work on this activity line. It is because those droplets, you see, they are 1 to 10 microns. They are very small. And when you prepare them, this is really a tank. Could be big like that. Water, a droplet, you do that. And you have an emulsion of droplets. So then, and the droplets they are flow, they are moving. And even if you wait, there is small particles, there is Brownian motion. Some of them will sediment or going up because of buoyancy. So how to deal with that in an optical setup? It's not that easy. You can take them, put them between two substrates, and then to illuminate them. This is one option. The option we were using here, it was like somehow lazy option in the sense that by using a tweezer, the system, we even do not need to align the system. A droplet is passing by the tweezer. There is a tweezer. It is trapped and it is self-aligned. So it is very practical because your vortex plate is self-aligned to your beam. There is no optical alignment. Light matter interaction is aligning your system. So optical tweezer was a very convenient way to have a reproducible alignment, light with matter, in order to make a very robust experimental assessment of this first demonstration, actually.
So why I have asked the question is like when we generally do the theoretical analysis of this vortex generation, like in there we consider this is like a paraxial light interaction with the space, like inhomogeneous anisotropic. But
Yes.
like in tweezers and all, like if we are tightly focusing, it's like it is kind of like non-paraxial beam interacting with this inhomogeneous. That can be the spin orbit interaction there can be complex somehow. So
exactly. So exactly. So it's a very good point. And so why this remains of interest, I would say, and why this was somehow qualitatively appealing here to work with the non-paraxial beam. So there is this self-alignment. So this is from practical point of view, and from the fundamental point of view, this shows that what matters is the symmetry. What matters is the topology. I mean by that you see here, the NA we were using was 1.3, if I remember properly, or something like that in that work, which is a very standard numerical aperture for highly non-paraxial beams used in optical tweezers experiments. Anyway, the shaping of the output light field was qualitatively fitting with this paraxial description, which means that what matters here in terms of the robustness of the optical phase singularity shaping at the first order is the transverse component and not of the light field, and not the longitudinal component associated with non-paraxiality. Of course, if you go in the detail of light-matter interaction in that case, it will be much more complex. And by the simple presence of the non-paraxiality, the focused field itself, it's already a mixture of optical vortices due to non-paraxial corrections. So the global picture is much more complicated than the simple qualitative approach here I was delivering for capturing the essence of the topological shaping. In practice, you will have fine, delicate contribution associated with non-paraxiality. Of course, yes.
Thank you.
And it's even more complicated than a uniform plate illuminated with highly non-paraxial field, because here it's a droplet, so it is also a finite size object, so with a 3D distribution of the optical axis. So you can imagine how complex is the reality of this light-matter interaction.
Yes. See you for that. So if there are no more questions, then let's thank Professor Etiennne Brasselet. So thank you, Professor, very much for this wonderful talk, and we will really like to have you here in our campus maybe someday, if when this pandemic goes over and the travel is allowed. I will really want you to deliver a presentation.
It would be a pleasure if we can do that later, yes.
So thank you and have a good day.
Thank you very much. So bye-bye to everyone, and enjoy science and photonics.
Cheers.
Bye-bye.
Bye.